I'm sharing the screen. So this lesson I have given the name life table and R, right? You can see the R because finally we will be finishing at R. Right? Whatever you do, you may go by Euler method, or you may go by just and not ERT method, that is the geometric progression. Whatever, you will end up with R. And as you know, once we get the R, we can easily predict the population, future of the population. So this is why I have taken this lesson is life table and R. This is a table that is familiar to you. You can see those are the first class. I remember few were not there. So here you can see the age 0, 1, 2, 3, 4, 5. I have taken 2 more ages than that example I taught in the class. And again you can see the numbers 600, 420, 300, 150, 60, 0. And Bx, nothing to do. This is a reproductive potentiality. As the age increases, the Bx goes down. And initially, when they are young ones, they are not sexually matured. At the time, the reproductive potentiality is nil. Then you can go for Lx. That this Lx, as you know, Lx is Sx by S0, whatever it is 0. So definitely this is 1. X is 600, 0 also 600. So 600 by 600, it becomes 1. Then you come to X is 420 and 0 is 600. So it comes around, it comes the Sx by 420 by 600, right? So this is all these ratios were calculated that way, divided by 600. Then you can come to Gx, which is 1 x plus 1, Lx plus 1 divided by Lx. So Lx, x, this is the x. And you can see the Lx column. What is Lx column? This is Lx. Suppose this is Lx column 0.70. Lx plus 1. Now Lx, suppose we are calculating for this column. This is Lx plus 1 by Lx. Means what? You can make the ratio. Lx plus 1 is this Lx plus 1 by Lx. So definitely last one will be 0 because this one is 0. Plus 1 is 0. The last one is 0. And Lx by Bx. This is the one of the derivation that we can have for calculation. We'll come to know what is the use of this Lx by Bx. Then you can come to the Lx Bx x. This you can have here 0, 2, 8, 3 like this. So this is a general table that you may have initially. Sorry, this is Lx Bx, okay, Lx Bx, not by. This is Lx Bx x, okay, x. So this is what your total table, the first preliminary table that you can have. Once you have this data from this particular, you can see the particular this zone, this data 600, 420, 300, 150 and 60. If this data is given, you can have all these derived data you can generate from this Sx. Then if Bx is given, you can easily calculate these two columns, Bx, right? So overall, this is the first table that you can easily prepare, and we can move for the next table. Right. So is it clear? This table is clear to you? Anybody else? Any doubt in this table? So now let us go for the next what is interpretation. This now table is familiar to you. Okay, this table is familiar to you, that we have, you can remember this one, right? You can remember this one. All these are same, right? These are same. Now what is new here? As you can see, what is new here, this particular R naught. R naught is 4.90. This is sum of all this LX BX. All the LX BX, you can make a sum up of this one, you'll get the R naught. This you add one by one, you'll get R naught. Then LX BX X also, this is LX BX X, right? This is multiplication of all this one. Also you can sum up, it is 7.70. So here, this is the generation time, which is calculated as LXBX X. Sorry, this is not divided by LXBX X and LXBX. So you will get a 1.57. Now, why we're coming to generation time? If you remember, you can remember that N naught E N T N naught ERT is formula we just discussed in the class regarding how to get the R. There we found Z naught, right? Z naught we found, and Z naught is equivalent to, you can say, the generation time. But since it is a you can say the geometric mathematical relation we have used, this is not directly applied to the population, human population. So we have to make some corrections, and that is why. But our basis is this Z naught, which we have derived from this particular geometric progression. So this Z naught is now 1.57. Now this 1.57 that you have seen, we have got it from the R naught and the summation of LXBX X. So these two variables have given Z naught, right? Now what we do, Z naught, again you can see here, Z naught we are using it for the R, right? R, calculation of R. It is ln R naught by Z. So once you get the Z, R naught you are very clear, R naught 4.90. Then your Z is also clear, 1.57. Now you got 1.01. This is our uncorrected R. Uncorrected R means, you know that we have discussed a lot about Euler correction. Before Euler correction, this is our R. Clear? So is it clear to you how we have got the R for this time? Uncorrected R. This is our uncorrected. Yeah?
Sir, please again tell sir LX, how to find LX, sir?
This LX.
Yes,
This
sir.
one.
Yes,
This one. This one LX. Right?
yes, sir.
Okay. LX is. Let me go back to the previous table. This is LX. Okay. Now see, this is X. Right? All are X. X is equal 0, X is equal 1, X is equal 2. Clear? And this is Sx. Now your Lx is equal Sx divided by S0. What is S0? S0 is always 600. And X is changing. See, this is 1. Now here Sx is 2. Here Sx is 3. 4. So what is that? 420. It is equivalent to 420. 300, right?
Yes.
So now let us go to, we got the R, see, uncorrected R. Now what to do with the R then? Say for example, our R is 1.01, or you can say it is 1.0. Clear? Very simplified, we have made a very simple one, 1.0. So the table is same. You can see this is the same column. This column is same, this column is same, all columns are same. Now we have a new column here, right? What is that? This is e to the power rx lx bx. See, this is this particular expression, and if you remember, this is an expression we got from Euler equation, right? e to the power minus rx exponential actually rx lx bx. So here r we have considered 1.0. So here you can see x is this one 0. This is x 0. So in this particular expression, you see, just I'm giving it down here, e minus rx, this particular part, lx bx, obviously lx bx is this one, lx bx is this one. So this is lx bx. Okay, so you can see r, this r is 1, this r is 1, right? This r is 1, so we can write here what, this minus 1. Now x is 0, right? X is 0. Here you can write 0. So it is minus 1 into 0. And lx bx is also 0. This part is also, this is 0. Because this is lx bx is 0. Now what is, you can find the second one similarly, e minus 1 into 1. Because this is x is 1, right? You can see the left hand, your left hand side 1. So minus 1, definitely first one is r, second one is the x. So lx bx is 2.80, right? Then again third one you can now understand, minus 1 into 2 and lx bx is 1.50. Similarly you can find out into 3 0.50, into 4 0.10. This is our initial estimate, as we have calculated from the uncorrected one, initial estimate, how to make it, right? So this is first one we have got, that we have constructed, initial estimate. Let us go for the a little bit detail. So once you calculate, as in the previous one, if you just you can take the help of your any online calculator, or you can take the help of your scientific calculator. You can find what is the this 2.37, mostly 2.2387. I forgot the number of value of e, right? Just remember number 2 point something it was, and
2.7187.
right, 7187. So this to the power minus 1, this to the power minus 2. Likewise you can go on from calculating the whole these expressions, you'll get the data. It will come like this, right? It's come like this. Okay, so this, when you multiply with the lx bx, this is your outcome. This is your outcome for every x, right? You have a outcome. Since there is no lx bx in this part, we don't have any data here. Now you can add up all these initial estimates we got. There is a, we have some cross-check rule. Say for example that we got the r is equal 1.0, the rough estimation. Now this 1.0 estimation, whether this 1.0 is actually representing the r for correction, because there are cross checks. If you go on calculating this also, if you go on calculating, as I told you, one time will come that the things will stabilize, but you cannot continue it indefinitely. How long will continue? How long you will go on calculating this whole table with a new set of population to get a stabilized r? For that, there is a shortcut cross-check method which is called Euler R. Euler says that summation of ERX, LX, BX is always 1. Right? Euler says that summation of e to the power rx, exponential rx, negative rx, lx, bx is always 1. So what we are trying, summation of this one is not 1 now. It is 1.2596. So this, if we have to agree with Euler, we have to make it 1. Now you can see this one. Can you see these figures? Right? See, this is what I just made this -1, as we know that -1. This is the R we got. This is the R minus, no, you have E minus Rx, right? Rx, this was Lx bx. Lx bx, this is the formula. So this is R minus 1. This is X, 1, 2, 3, 4, X. So when you multiply these two, Rx, you are getting this one, Rx. This is Rx, minus Rx, right? So now the Rx, when you make this power of 2.817, this is coming the final data, right? Then you can come multiply with Lx bx of these two, right? This is 2.8. You remember 2.80, 1.50, 0.5, 0.1, right? That was our outcome. This is what we got from the uncorrected one. So when we add all these things, our total is 1.25997 something else. Now we have to make it 1.00, means this thing should go. How we have made it? So this is one. See, there is just one experiment. This is already I have done after trial and error method. Suppose this particular number, how it can make it? Can go there. Now see, this is the total number. This is the sum, 1.25. Just make it, because you can change the R. You cannot change anything else, right? You have to adjust the R. This R you have to adjust. You cannot change anything. So you can make a try. 1. Suppose I am giving 4, 5, 6 or 4, 1.4, just randomly. See, this has come to 0.92. It means it is less than 1. Right? If I use this one, whole thing, it is 0.7. I cannot get 1.0. So I have to take something which is less than 4. 2 I am taking here. So it is going 0.9. 0.99. So it is, when I am taking 2, this is the 2 here, I am getting 0.99. Rather, I can take 1.1. So it is coming 1 point something, 1.117. So it is reduced, right? Your 1.2597, this was the figure. Now it is reduced to 1.117. So it means if I cannot change the first digit number, it is 1. Then I have to go for the second digit number. Let me start from the highest number, 9. See, the second digit changes. Here, 00, 1.00. So you can get the idea how you can make it 1.00. You can go on doing experiments. So I have taken 3 digits, 4 digits, sorry, minus 1.195. 1949, but it is 195. When I converted to 3 digits, it is 1.195. This is how I did with trial and error method. So finally I got it is 1.000. If it is to be 1.000, then this number should be 848. First one should be 848. Second one should be 137. Third one should be 014. Fourth one will be 001. So your all this will change, right? All this will change. It will come 848. It will be 137. It will be 014. It is 001. Yeah. So here we can go with the same logic. So you can see 848, 137 there. Right. 848, 137, 014, 001, it is 1. So our corrected after R from Euler computation, it is 1.193. So what is the correction factor we have added? 0.195. Right? That you can make 195. That is 195. Sorry, 195. we have taken, this 1 becomes 1.1. If instead of suppose r, this as I told you that 1 minute, this r which we have taken 1, if we take r is equal 1.195 instead of 1, we will get here this particular part as 1.000, right? 1.000. Here we have taken 1 as r, right? Previously, see, this is 1 as r. So this 1 we have taken r. Rough estimate of r we have taken -1. This rough estimate. After doing Euler's permutation, we got that it should be 1.195, right? If we replace 1 with 195, we will get 1. So means the corrected r is actually 1.195. So your Euler term is fulfilled, condition is fulfilled. So you can take this 1.195 as your estimated r, corrected r, right? Now the same thing you can do with the help of Lashley matrix. The Lashley matrix you can do the same thing, but difference is that Lashley matrix, once you go on calculating with this way, whatever I have taught, you have to continue few generations. Then one time will come, this is estimating r from Lashley matrix, that particular lambda will become stabilized, and at time you will get this r, and it will be for your this population, whatever we have taken example is 1.195. Again you come to the same expression, 600 bx 1.0 gx, same thing, but here there is one new thing, pi equal li by li minus 1. This is one column, right? This is column. Now you may have a question, why it happens. In Lashley matrix we are calculating the population where the population has some increments. So in the first case we don't have any increments because the reproductive potential is 0. So our starting point is x1, right? When time 1 is there, when n1 is there, our starting point is n1. So we will represent n naught, which is the 0 time, from this particular range, not from this range. So in that case, this gx, you remember gx, which is lx plus 1 by lx, may not work. We have to come down one step down. One step down means we cannot take this one because there's 0. It is 0. We have to come down one step. So here, that is why this pi has been formulated. Pi is li by li minus 1. The expression is same. If you compare with gx, it is same. But the benefit is that now it is corresponding to the L1, not 0. So here you can see when you calculate this one, you are getting pi is 0.7, 0.71, the same thing. The li, this is li, this particular column, if you consider li, this is your li minus 1, it is 70. Then li, this is your li minus 1, your 7.1. Likewise you go down, and finally you are finishing at the same 0, 0. So there is no technical problem, but you have shifted your calculation from this 0 to 1 and 4, 5. Right? So this is what pi we have done. Then you can go for fi. Right? Fi, which is another parameter that we need to calculate. This fi is bi into pi. So definitely your bi is given. Now you got pi, so you can make it bi multiplied by pi. Right? I will show you that actually heading has gone out of the range. Yes, this is bi pi. Okay. So this is one, you can get it. Now your calculation comes here. This is your calculation. N1 t plus 1. As I told you that when the first time starts, when you are at 1, you may have the all reproductive ages. Maybe the all ages are there. Starting the young ones are there, middle aged people are there, old aged people are there. So all ages are there, all reproductive populations are there. So we have to add all F1, N1 to F2, N2 to F2, N3, because at different times they have a different ability of reproducing. But in starting period, when you have started counting the population, today say for example, they are all present in the population. So you are adding them up. Total you will get something, summation of something, so you are adding them up. But when you go for a next population, that population will be the first population. Now you are, since you have already started with the population, your next population will be this population, right? This P1, right? So P1 will be your reproductive ability, clear? So then P2, P3, P4, we will get it, because this will be cumulatively added to all these. When you do the matrix, whatever it is there, this will be cumulatively added to all these. But you need to first count all together at once, then you can go on computing the matrix. So matrix structure, you can see already, you know the structure. First you have to write F1, F2, then the P1, P2, P3, P4, likewise whatever number, 1, 2, 3, 4, your 5. So this is 1, 2, 3, 4, 5. It is it is known as F into F matrix or N into F matrix. What? 1, 2, 3, 4, 5. So N into N or F into F, whatever you say, this is the matrix, then you will get it. Right? So your matrix is ready now, and you have already computed your required data using R, Euler's corrections. Let us arrange it. So see, this is the same thing we have arranged. What we have arranged here, already have computed, right? Already computed this one. 2.80, 1.13, 1.0, this is 2. Okay, sorry. This is 2.13, right? 2.13, right? 2.13. Likewise, 0.70, 0.70, 0.71, 0.71, 0.5, 0.4. So our matrix is ready. Now you can go for multiplication. Matrix multiplication is very, that same only one procedure you can apply. Right. So here there may be something wrong that I want 1.13. I used 2.1 instead of 2.13. Whatever. This is the F1 and F, and this is the P, all P1, P2, P3. And suppose 5th year, you have to count for 5 years. 5th year, after 5 years of this population, this is counted at 0 time, and after 5 year, you have this data. Now the question is how the population will progress. What is the population of that particular structure of population, a particular time? So we have say n is equal 5, n 5, and t is equal 5. So we have to count every t plus 1 means the first population, t plus 2 you get the second population, t plus 3 you get the third population. So you have to go on counting, and when you go first population, this one, then second population, t plus 1, first population, second population, third population, fourth population, fifth population. So you have all matrix values ready now. You just count it, how much comes. So that, now remember, these are not total number. We are counting the matrix. This is a vector for this Leslie matrix. Do not confuse that we are counting the total population. Actually, we are preparing the matrix for our vector for the Leslie matrix. This is the best matrix of Leslie, but here our vector is n5. After 5 years, the population is 250, 100, 50, 25, and 10. 1, 2, 3, 4, 5. All different age groups. Right? So what would be the matrix matrix structure. So you will get a structure from here. You can count it, you will get a matrix structure from here. I'm not repeating how to count it because already you know that this one into 250, this one into 100, this one into 50. Likewise, you have to go on. Similarly, this one into 250, second one into 100. Likewise, same repetition you have to go, and finally you will find this another 5 this type of vectors here, vector components here. Right. So here, whatever you get in that particular component, suppose A1, A2, A3, A4, A5. Suppose you've got 5 values. You can go there, you can put A1, A2, A3, A4, A5, right? That you can put. So it is your new vector. Right? Then again, see the earlier what you got? This vector A1, A2, A3, A4, A5. You make a total of the first one, N naught, N0, right? And NT, you are getting this one. Right? So this is N naught or N0, and this, suppose this is A total. Now your lambda will be what? See the N total T time or N total T minus 1. So your AT divided by 435. This is lambda. And your R will be ln lambda. Whatever value you will get, you put here ln k. This is your final lambda. So is it clear to you? Lambda, now you are actually now after putting in the, it is not 1.195, it is not 1.0, right? Your R value is coming from lambda now. And this R value you can have every time you do the vector, recalculate vector. Suppose after 10 years you calculate the population. So you have the best, this best Lichley matrix. You can compute the R at any moment. And remember why this R is most important from lambda, because when the time progresses, the resources are changing. Sometimes the resources were more, means the R is very, very high. If the resources are limited, R will be reduced. So that you can compute from this data. But your basic data will be from this Lichley matrix. So this is, we have got uncorrected R, Euler R, and finally we got the lambda R, right? This is what the computation you can do. That this is directly I have taken from the Gotelli. So estimating R from Lichley matrix, right? That if it is readable, you can see. So you have estimated R uncorrected, and then you have estimated R from Euler. I mean, actually R is fixed from Euler. Then that R you have used for preparing the matrix, and finally using the matrix you are finalizing the R. This is, so your lambda was this one, and at a time this is not going to change. And what I believe, if you go on computing this one, one time will come this Euler R and Lichley matrix R will almost same. It's almost more or less equal. It will remain more or less equal, right? Because of the decimal things, it may vary slightly, but it will remain equal.